Hi everyone, my name is Tejas Chopra, and today I'll be talking about how you can move from 99.9 or three nines of availability to four nines of availability using Kafka. The agenda for the talk today is I'll give a brief introduction about what I do, some of the problems with cloud storage and ways around it. Then we'll go into what exactly is availability and how do you design systems that have three nines of availability and how you can change the systems that have now four nines of availability. Finally, there'll be some takeaways and lessons from this entire journey. I'm a senior software engineer at Netflix. I work with the data storage platform group at Netflix, and my job is to architect storage and infrastructure solutions to support the exabyte scale data and billions of assets that are produced and managed by Netflix studios and streaming platforms. Along with that, I'm also an international keynote speaker. I talk on cloud, distributed systems, blockchain. Prior to Netflix, I was a senior software engineer at Box, where again, I was architecting infrastructure solutions and storage in cloud to support millions of customers and petabytes of data. I have worked in companies such as Datrium, Samsung, Tensilica, and Apple. So a lot of companies and a lot of organizations are moving to cloud, and we are seeing that the footprint of data in cloud is now growing, and it's probably reaching a zettabyte, which is a billion exabytes. Um, One thing to note is that as the organizations are moving to cloud, they are also facing the dilemma of prices and availability of cloud. So, for example, one thing to see is that it is very cheap to put data into cloud, but you actually have to pay to send a request to cloud. So there is a cost of the request, there's a cost of storing the data, and there is a cost to read the data out as well. In fact, the cost to read the data out, which is egress cost, is pretty significant. Now, for example, here's a table that compares the different major cloud providers and what it takes to read the data out from their environment, from the cloud. And if you see for 10 terabytes, it's around $900 to $1,200 really that it takes to read the data out. And this is not the storage cost. For 50 terabytes of data, it's actually 3,500 roughly to 4,000. And for 100 terabytes, it goes to like $7,000 to $8,000. Um, Now imagine if you have an organization such as Box, which has petabytes of data, or Netflix that has exabytes of data, and that data has to be read out. It'll be just billions of dollars uh, of cost just to read the data out every single time. So the industry has come up with a solution to solve this problem, and that is like many other problems that get solved by the same solution. It's caching. So what the industry has converged to is storing a copy of data on premise. On premise means a hardware or a system that is owned by the enterprise. And so what that does is when you write data, you push it to cloud, but when you read data, you read it from on premise. It saves on the egress cost of reads. And one way to look at it is that the hot data, the data that is accessed more frequently, can be on premise, and the archived data can be on cloud. There are implications with doing that as well, because one thing is that with cloud you have a higher latency compared to on premise, so your reads will have better latency, and also security, because the data that you're having in your environment is feels more secure than the data that you've pushed to cloud, which is available to everyone in some ways. Of course, there's encryption and other techniques that cloud providers provide to secure your data there as well. But for organizations such as banks or healthcare, it's very critical that they own their data. So by employing this technique of storing a copy of data locally, organizations have been able to save millions of dollars per year. At Netflix itself, we are seeing like more than hundreds of millions of dollars saved over the next 5 to 10 years just by employing such strategies. So now coming back to availability of data. So availability is actually the amount of time your data is accessible. So if you look at on-premise systems, which is hardware that you own, typically availability is measured in terms of the nines. So 99.9 is the availability for on-premise systems, which means that for 99.9% of the minutes in a day or in a year, the data is available and accessible for on-premise. For cloud, they claim that it is four nines of availability, which is 99.99%. You may wonder what's the difference between 99.9 and 99.99. Actually, it is pretty significant. If you look at the numbers, comparing the availability, for a year, when you have 99% availability, it means that you can actually not be available for around 3 days, 15 hours. When you have 99.9% availability, you will be unavailable. Your service will be unavailable and your applications cannot read the data for 8 hours and 45 minutes in a year. And when you have 99.99%, it's like 52 minutes. So as you go 1-9, it actually exponentially reduces the amount of time that you're down. So Gartner actually calculated the average cost of downtime for organizations, and it is around $5,600 per minute, which means that if you have 99.9% availability, you're already losing $2.8 million every year. And if you have 99.99% availability, it is 290K dollars. So this is a great motivation for any organization to move from 3 nines of availability to 4 nines of availability. So let us now get into how would you design a 99.9% solution, or how we designed it first. And we have some on-premise system, which I explained is needed for reads, and we have cloud. And in this case, I'm using AWS cloud, but it can be any cloud. The upload request from a client to upload a file first goes to the on-premise system. The upload is then handled by the on-premise system. You upload it to a local storage, and then you get back success from the local storage. And then there is a Kafka queue, which actually takes that uploaded object and then gets information from it. And there's a daemon that actually puts the event into the queue and reads the event from the queue. Once you actually read the event from the Kafka queue, you use that event to trigger an upload to cloud. So in some sense, your cloud upload is happening asynchronously, and your local storage upload is happening synchronously. In that way, you are actually getting the response back sooner, but you're also hydrating the data on the cloud. And the way reads are served is, read is done from on-premise if it is present. And if, for some reason the data is not on-premise because it was not hot data, then read goes to the cloud. Now, the problem with this approach is that your uploads are happening to on-premise and then they're returning back. On-premise has 99.9% availability. So by default, all your uploads have 99.9% availability, which means that you may have times which is around 8 hours that you'll be down. So that's the problem with this approach. And then we move to a 99.99% solution. What this meant is we wanted to leverage cloud in the primary path of uploads and not do it asynchronously. And the way we used Kafka to do this was, an upload would actually split the stream at the client to upload to both on-premise and cloud. And that meant that you can actually get the benefit of a primary upload to cloud. Now, because on-premise has only 3 nines and cloud has 4 nines of availability, there'll be some uploads that have failed to go to on-premise but have succeeded in cloud. For all those kinds of uploads, you actually queue these uploads in a Kafka queue, and then you hydrate your on-premise system with the failed uploads from cloud. So this is where we leveraged Kafka, because Kafka gave us a great architecture for event streaming and a great architecture for driving our asynchronous workflows. And initially, when we started, we had a lot of uploads that had failed for local storage. So Kafka, because of its scale and because of its retention, we were able to, hydrate our local storage with all the failed uploads. And the reads get served again in the same way. You try to read from on-premise first. If it doesn't exist, you try to download from cloud. So this is how Kafka helped us in our use case here. So what were some of the takeaways and lessons from this? Uh, so there were millions of customers that we had and billions of files that were uploaded. And there were a bunch of, like, hundreds of thousands of files that actually failed to upload to local storage, but succeeded in uploading to cloud. So for those files, because we had to push them to queue, Kafka scale was very critical. And Kafka scales without any downtime. Kafka throughput is in fact thousands of messages per second, which was really significant in order to get our hydration done quickly. And that meant saving more dollars because the reads will then be served from on-premise. For the files that are not hydrated, the reads would have to fall back to cloud because that's where the primary copy is also present. And so we estimated that it saved us hundreds of thousands of dollars by employing Kafka versus employing other alternatives such as Kinesis. Kafka persistence compared to Kinesis is very critical in designing the rehydration strategies. I think Kinesis has a persistence of around 7 days. Kafka is persisting for around, you can set the persistence. So that was very important when we had issues and bugs and we could not rehydrate correctly. At least we were sure that the events and the messages are still in Kafka. And we did not have to process the files again on cloud. That saves a lot of engineering effort, and it also saves a lot of time to write a daemon that iterates over all the objects in the cloud to rehydrate. Uh, Kafka provides batch handling abilities, and that was very useful for non-critical data such as thumbnails. So with every file that gets uploaded to either Google Drive or Box, there's a thumbnail associated with the file that shows you exactly that small image of the file that you've uploaded. And that is not really critical data. The critical data is generally the file itself. So this is the metadata for the file. So using batch abilities of Kafka, we were able to batch a lot of these thumbnails together and gave better performance. So tracking of offsets in a partition is generally left to the consumers was one of our learnings from Kafka. And it took some time to implement that as well. The other thing is Kafka comes with its own cluster management. So you have to have your own Kafka cluster. You have to figure out Zookeeper and other primitives that on which Kafka is built. And so that is another thing that you have to be mindful of when you're designing systems. Um, so that's my talk. Thank you so much. Please feel free to reach out to me on my email, LinkedIn, and Twitter. And I'll just put a plug in here that Netflix is hiring in the US. So please, if you're interested in challenges of distributed systems, storage, cloud storage, feel free to reach out to me and we can always discuss more. Thank you.